Okay, so let's get started. What we're going to do right now is just a quick review of the material that you should already know from discrete structures. Um, you should do the exercises that I've assigned you in the book that have the answers in the back of the book just to confirm that you're prepared for Foundations of Computer Science. And I'm going to not try and teach you all this stuff. This really is intended to be a review. So if there's something that you don't understand, you need to review the material and you can ask some clarification questions if you have any. But if it turns out that there's a lot of material that you don't understand or remember, then you really need to drop this course and take the previous course, Discrete Structures. So we're going to start with 1.1.1, which is statements and truth tables. And this should be really old hat to you. Right now we're going to talk about negation when you put a not in front of something. I tend to use this notation for not. Your textbook is just using the word not, so we're going to use this in many of my slides. This is a common notation here. It says Dr. K's notation, but really this is a notation that lots of people use, just not your book. So if S is a statement, like the Phillies are the best baseball team, then the negation of S, not S, very formally is it's not the case that the Phillies are the best baseball team. Colloquially, we might just say the Phillies are not the best baseball team, or it's not the case that the Phillies are the best baseball team. But you should, of course, be familiar with this kind of a truth table. Since we're doing not, we just have one statement S, which is true or false. And if S is true, then the negation of S, not S, is false. If S is false, then the negation of S, not S, is true. Here is the truth table for conjunction. Conjunction is just a fancy name for and. If we have two statements, now we're calling our statements A and B. The rec center is a great place to visit is A. B is the student center is a great place to visit. Then formally, the conjunction of A and B is simply the rec center is a great place to visit and the student center is a great place to visit. Colloquially, if we're just saying it in English, we might say the rec center and student center are both great places to visit. And again, this is a fairly common notation using this sort of caret notation to represent and. Your book just uses the word and. And here's the truth table for A and B. You should be very familiar with this. If both A and B are true, then the truth table reports true. For anything else, if either A or B is false, then A and B is false. Here's the truth table for disjunction. That's another fancy word for or. So this is A or B. I use this notation, the kind of V notation here for A or B. Again, that's not just my notation. That's a very common notation. You probably used it in discrete. If we use the same two statements for A and B, A or B formally, we just put the word or between the two statements, but colloquially, we might say the rec center and or the student center are great places to visit, right? Because with our truth table, if you look, a truth table for two statements, if you're doing the disjunction, figuring out or of them, is always true unless both of them are false. So logical or is really A or B or both. If either of them are true, the result is true. Here's the truth table for if A then B. Sometimes people call this conditional or implies. We'll use this arrow notation. Again, a very common notation, even though your book isn't using it. So we might have a new statement A, a person regularly gets 8 hours of sleep a night, and a statement B, a person is well rested. So if A then B formally is just if statement A, then statement B. Colloquially, we might say something like people who regularly get 8 hours of sleep a night are well rested. And here's the truth table for if A then B. This one's a little bit weirder. People find this a little bit harder. The thing to remember is it's always true unless the A, the if part, is true, and the B, the then part, is false. Under those conditions, we end up with false. So conditionals end up with some weird things that may not make sense if you think about them too hard, but it works for the conditional. It's right for the conditional. So for example, if statement A is the moon is made of green cheese, and statement B is I will understand foundations without studying. Well, if the moon is made of green cheese, then I will understand foundations without studying. That is a true statement. This implication is true because the moon isn't made of green cheese, but who cares, right? It doesn't actually tell us anything we need to know. For logical equivalences, when two things are logically the same, right? Here's De Morgan's laws. You should remember De Morgan's laws. Here's how your book is writing De Morgan's. And here's how I'll write it. So I will just write it with my logical symbols. But what you need to know for this is I'm using this triple equal sign for equivalent, right? So that's just my notation that I'm going to use on these slides. And your book tends to write it out. So here are the two De Morgan laws, which should be very familiar for you. And here's a bunch more logical equivalences. Of course, there's an infinite number of them. To prove one of these logical equivalences, you have a couple of choices. One choice is you could just do a truth table for the thing on the left and do a truth table for the thing on the right. And notice that both truth tables actually have the same result for each option of A and B, whether A is true or false and B is true or false. Another way is you can do a formal proof, and we'll be doing more of those later. For now, I want you to take a look at each of the rows on this slide and make sure that they make sense to you. The first two are, of course, De Morgan's laws again. And then you have some more logical equivalences that can be useful. They can help us in doing some proofs. Okay, so we're on to 1.1.2, something to talk about. This is just a section that's going to give us some things to write proofs about. In this case, we're going to write proofs about the integers. So the integers is the infinite sequence of numbers, negative, 0, positive, all whole numbers, right? And we're going to talk about an integer dividing another integer. So d divides an integer n if d isn't 0, and for some integer k, n is d times k, right? And the book and I actually agree on notation for this one, so this says d divides n. So here's a couple of divisibility properties. I want you to just look at this and say, yeah, that looks right to me. So if d divides a and also a divides b, then d, of course, divides b. This second line, a little bit more, well, a little bit less intuitive, but take a look at it for a minute, pause if necessary, and say, yeah, I buy that. Okay. We're also going to want to write proofs about prime numbers, so let's just define a prime number. An integer p greater than 1 is called a prime number if both 1 and p are its only positive divisors. We're going to go with the book's definition of prime numbers. That's what this is. Whenever possible, I'm going to try and stick with the book just so that I can be consistent and to make it easier for you. And so under this definition, we have to say that the number 1 is not prime because the only integers that can be prime are integers that are greater than 1. So let's talk about a couple different proof techniques. Again, these are proof techniques that you should already know. So if you have a finite number of things to check, you can do proof by exhaustive checking. So if I'm teaching in a classroom and I make the statement, one person in this classroom has a quarter in his or her pocket, I can get everyone in my class to turn out their pockets and see if anybody has a quarter in it. And if there's a quarter, then the statement is true. If there's no quarter, then the statement is false. Similarly, we can look at the statement, there exists an integer between 0 and 100 that's divisible by 5. Well, we could just start looking at all the integers between 0 and 100. I haven't been very specific here. I haven't said whether I'm including 0 and 100 or not, but let's start with 1. Nope, not divisible by 5. 2, nope, not divisible by 5. But we get to 5 and we say, oh, yep, 5 is divisible by 5, so the statement is true. We can also disprove by exhaustive checking. So, I mean, that's just finding a counterexample, right? If I make a statement that says, no one in this classroom wears glasses, we can look at every single person in the room, and if there's somebody in the room wearing glasses, we can disprove that statement. Similarly, the statement that every odd number is prime, well, we can start looking, and if we can find any sort of counterexample, then we're good. So there are in fact an infinite number of odd numbers, but if we find an example of an odd number that's not prime, then we've disproven the statement. So, if we start at 3, for example, ignoring the fact that 1 already is not prime, so that's already disproven the statement. If we just use 1, we could say 3, well, that's prime. 5, that's prime 2. 7, that's prime 2. 9, oh, there's another example of something that's not prime. Of course, we only need one example that shows that the statement is not true to show that the statement is not true. Okay. Another kind of proof is a conditional proof, if A, then B. There are two typical approaches for this. Sometimes we use the direct approach, which is simply to assume A is true, right? If A is true, so assume A is true. And then follow a logical sequence of conclusions to demonstrate that if you assume that A is true, B has to be true as well. There's also, it's a very common technique to use proof via contrapositive. So this is kind of like following a maze or solving a maze by starting it backwards. Remember that if A then B is exactly the same. It's equivalent to not B implies not A. So if not B, then we know not A is true. So if you want to prove via contrapositive, you just start by assuming B is false. Assume not B. And if you can follow a logical sequence of conclusions to prove that A is also false under those circumstances, then you've also proven if A then B. Proof by contradiction is one of my favorite methods of proof. You want to prove some statement S, and the general way to do this is you assume S is false, and then you follow some logical sequence of conclusions to demonstrate that a contradiction occurs. So if S is false, then the moon is made of green cheese. Well, we know the moon is not made of green cheese. And so the only thing we can do is say that our assumption that S was false isn't the case, and so S must be true. Now, proof by contradiction confuses a lot of people, but it really shouldn't. It is really easy to write a good proof by contradiction, at least outline. You need to do some smart stuff in the middle of your proof sometimes, but really you should just copy down this outline, this proof by contradiction cheat sheet, I call it, and you will do fine. So, for example, what you do is you write statement, and then you fill in your statement. And then you just write these words next in your proof. Let's assume the statement is false. That is, and you put in the negation of the statement here, right? Not of the statement. And then you write again on your paper. Then it logically follows that. And now you got to do the really clever stuff so that you end up with a contradiction. So you get, say, 1 equals 2, or the sky is, I don't know, pink with purple polka dots or whatever. At which point you write contradiction. And you have to tell me that you found a contradiction. Or you can draw this. It's supposed to kind of look like 4 arrowheads banging into each other. I'm not sure if I think it looks like that, but I like this symbol. I think it's kind of cool. And then you write, thus, we've proven by contradiction that, and you fill in your statement again, right? This is plug and chug, just put it in there. And once you are done a proof, you always need to write something at the end of the proof that says, look, I'm done. In my case, I'm going to write QED, okay? So here's an example of proof by contradiction, and let me just point out that I got an outline of this proof from this location that I've cited. It's always good to cite if you find something on the web or in a book. I was looking for, show me an easy proof by contradiction example that I could fit on a slide. And so I took the proof by contradiction example of the statement and put it into my outline. So here's my outline doing this proof by contradiction, all right? So the problem is prove that there is no greatest even integer, right? And here's my proof. And you can see that my proof is absolutely following my outline, right? So you say my statement, there is no greatest even integer. And then I write, let's assume the statement is false. That is, there exists a greatest even integer. Then it logically follows that, right? And here's my proof, and you can look at my proof. So for every even integer n, there must be some greatest even integer, right? So we're going to call it e, must be greater than or equal to n. And now let's think about the number that I'm just going to call m, which equals e plus 2. Well, m has to be even, since the sum of two even numbers is even. M must also be greater than e, since m is the same as e plus 2. But hang on, we've got m even, and we have m is greater than e, but by our assumption, m is also less than or equal to e. So m is greater than e. No, it's less than or equal to e. No, it's greater than e. No, it's less than or equal to e. We say, that's a contradiction. So we draw our little symbol, and so we say, thus, we have proved my contradiction that there is no greatest even integer, QED. Of course, when you do your real proof, you don't do it in red and black, you just do it in one color, but I did this to really emphasize how I'm just using my outline. Okay. Finally, there are if and only if proofs, at least the proofs that we expect you to know before you get to Foundations of Computer Science. Of course, there's lots of different kinds of proofs. And if you want to prove that it's the case that A if and only if B, most of the time, the easiest way to do this is assume A and prove B, and assume B and prove A. But once in a while, you can, in fact, do a proof where you start with A and you have a series of if and only if statements that end up with B at the end.